Without the supercomputers that we have today, we could not have developed the vaccines that we're using today for helping us cope with the COVID-19 epidemic. That's because there was supercomputers, and supercomputers need super chips, and that's what we do.
Welcome to 20-Minute Leaders. Just sit back, relax, and learn from the leaders of today. It's a journey. Each one is different, unique, inspiring. Let's get started. This episode is powered by J Ventures, a community-driven VC fund in Silicon Valley in partnership with Leumitech, sponsored by Homeward Ventures, Hippo Insurance, Upwest Labs, Synergy Global, Hillel at Stanford, Leap, Birthright Excel, Serona Partners, and in media partnership with CTech. Hello and welcome to 20-Minute Leaders. We're about to talk about chip design and semiconductors, and I'm really excited for this episode with Sandy Saper, ASIC Design Manager at Ready Group. Sandy Saper joined Ready in 2020 as ASIC and FPGA Design Manager. He brings over 20 years of experience in managing complex SoCs for wireless, communications, and automotive applications. His experience encompasses all aspects of the SoC development cycle, from requirements, specifications, architecture design, verification, circuit, backend, and silicon validation. Sandy has a proven record of managing multidisciplinary development teams and execution of projects efficiently and effectively. Prior to joining Ready, Sandy was Director of Engineering at Verisense. Before that, he was R&D Department Manager at Freescale Semiconductors. Sandy holds a B.Sc in Electrical Engineering from the Technion Institute of Technology in Haifa, Israel. Talking about chip design, semiconductors, engineering, at the end, designing the things that power, consumer behavior everywhere we go. Kind of a black box for me until recently, and I kind of fell in love with what's happening with chip design recently, and I'm really looking forward to hearing your personal experience, your own curiosity and interest in the field and what it's actually like to design chips. But before that, I'd love to hear a little bit about yourself, your career journey, and how you even got into chip design in the first place.
Okay, thank you very much. Well, I'm Sandy Saper. I've been 30 years in the development of chips. I manage a team, a hardware team that designs and develops chips for the semiconductor industry. I work at Ready, which is a private company in Israel. We have 200 engineers in the company. Half of the company is hardware in my team, and the other half is software under the software manager, which I'll get into later and to explain to you how important that is and the advantage that we bring into the market that we have under the same roof, hardware and software. That's a good question. How did I get into that? I was always interested in electricity as a teenager. And when I signed up for the university, I said, okay, let's go into electricity. It seems that it was back in the 80s, 1980s. And I said, that's where I want to be. I had no idea what chips were then. But during my studies, I started to learn about electricity and all the amazing things that it does, and started to learn about chip design. And we clicked. The two of us clicked. Me and chip design, we clicked. And ever since then, I've been in developing chips from the start. And I've been Now,
is this, I have to ask, the curiosity and the interest for electricity and chip design, did it stem from mainly the academic side of things, the challenge side of things, or what did you understand about where the world was going and how big of a role this was going to play into society, this idea of chip design? What had more weight for you?
I was more into listen to the academics and more into the hands-on and do it, you have an idea, get it done. And so it's a good question, Michael, because I really didn't think that back then, in my early 20s, where this was going to, where it was really going. Back then, The technologies were in their infancy. The chips that were being done in those times were very simple compared to what is going on today. But I would say that I had the insight, maybe you could say, and this is the area I wanted to get to. And we started, you could see in the beginning, when I finished the university, there were already low-end microcontrollers for simple tasks, for computers. Just then, the first laptops, the first desktops, were no laptops back then. The first desktops were being produced, and you could. There's Murphy's Law, if you know it. Murphy's Law means every year or two there's another shrink where you can combine more and more in one single chip. And as we know, the development.
I think Moore's law, but I also love Murphy's law.
You're right, sir. You're right. Moore's law, exactly. You're correct.
Murphy's law is what happens to me every day when I leave the house. That's for sure, though.
So it's Moore's law, and it's been going on ever since, right? And we've been cramming more and more functions in every chip, which has enabled us to get where we are today. And cramming more and more performance in a single chip is more and more challenging for the design engineers, for the architects, and for the electronic engineers that have to meet that challenge. Okay? And
right. And why is so, Sandy? In a very basic sense, why is it critical to today's world? Why is chip design still relevant to what's happening today? Because I'm looking at this magnificent device, the iPhone or my earphones, and I have these tiny chips that seem to be doing miraculous things. Why? What advancements do we still have to make?
Artificial intelligence is just starting now. Supercomputing is just starting. It's there, and we work on chips that are serving the artificial intelligence and supercomputer markets, right? And you meet artificial intelligence every day. Face recognition, voice recognition, for example, and supercomputing for medical. Okay, without the supercomputers that we have today, we could not have developed the vaccines that we are using today for helping us cope with the COVID-19 epidemic. That's because there is supercomputers, and supercomputers need super chips, and that's what we do.
Fantastic. Okay, tell me a little bit about Ready.
So Ready is, like I said, a company that has hardware and software. And when you want to develop a chip for the high-end market or even for the low-end market, you need to know, you come with requirements, and we understand your requirements. And we have there's a lot of disciplines in developing a chip. And it starts off with understanding your requirements to meet the performance that you need, and to meet your price that you need, and to meet your power that you need, especially today in the handsets and mobile. Power is critical. And so we have to have a team that understands the requirements and can execute on the performance that you need. And there are a lot of disciplines to make a chip that meets the requirements. It starts off with the architecture. How do I even put all these blocks together so that they will function with each other? What's going to be in hardware and what is going to be in software is very critical. Hardware is thousands of times faster than software. And still, you want to be able to enable the software because software is what controls what we need, etc. But there's always certain areas and features that a customer needs that has to be in hardware, and that's where we in Ready can decide for you, for the customer, what can be in hardware and what can be in software. We We understand what the performance that you need, and we do the partitioning and calculate what has to be in hardware and what can also be in software. The more that's in software, the more versatile your solution can be, but you won't meet your performance because a lot of it has to be in hardware. Okay. And then there's the architecture team decides how we're going to put this chip together and to meet the performance, and can work on it for, depending on the complexity of the chip, between a month, 3, 4, 5 months, half a year, to make sure that we are going to, the end product is going to meet what you need. And then there's a design team, which have their expertise on how to design each actual block to meet the performance that you need, meet the frequency, meet the power, meet the throughput, bandwidth. We're talking about bandwidth, how much speed I need to download, and you need to hear me, and it has to be real time. And then after the design works and is finished the design, there needs to be fully verified. So there's we have a good and high quality verification team to make sure that that what we have designed is going to fully work, and there are no bugs, 0 bugs. We cannot allow bugs in our chips, and I'll tell you that later why it's so critical that it's fully verified. And then we have to change all the code that was written. We have to translate that into the physical chip. Okay. And then there's the team there that does the translation, what we call compile, into the physical chip. And then we have to validate that the physical meets the requirements mainly of speed, the clock frequency, and the power. And then after that, every stage that I'm telling you about takes a few months, depending on the size of the chip. Smaller chips can take less time, but the larger chips, the ones for the artificial intelligence and the future, can take more time. And then we have to validate that what we have done is exact, and then we ship it off to the factory. And when we ship something off to the factory, it costs millions of dollars, depending on the process. It costs millions of dollars to just get into and prepare the chip for the factory, for the fab. We call them fabs. Okay. So yes,
I heard about that term before.
Oh yes,
now
fabs
I understand.
are like the highest technology factories that they really have in the world. Super clean, super high quality, very high quality. So here's the first thing: I cannot ship a chip that has a bug because it's going to cost me $1 million to fix it. Millions of dollars to fix it if I don't do it correctly. Plus the schedule, the time it takes to fabricate a high-end chip in the fab can take 3 to 4 months. And you want to get there, time to market is critical. So you will only, if, God forbid, you have a bug in your chip, you will only detect that when you get the silicon after 4 or 5 months. That's why it's critical that we have high-quality teams that make sure that there are no bugs in the flow. And that's what we have at Ready, an excellent team that does the verification, the design, the architecture, and the final product. And then after it's gone through all the stages in the factory, it needs to be packaged. And then we receive the chip and we validate that before we ship it to the customer, we validate that it meets all the performance that we designed it for, and meeting the frequency, power, before we ship it to the customer. And that can also take a few weeks to validate that everything is perfect and that, God forbid, you don't have a field failure.
I think it's incredible, and I can imagine how software. I'm coming from the software world, and I was taught, if as long as the bug is not huge, ship it, get users to start using it, and then roll an update in a few hours once you start getting some feedback. But there's no reason not to ship at least part of the features. But here you're saying the whole process is so lengthy and complicated and requires such a detail and such orientation to detail that if you ship a bug, the cost of the time to market, the cost in dollars to revisit the stores, to perhaps even recall things and to fix them is so grand that and it sounds like the amount of detail that you're dealing with is an incredible amount. I mean, then these chips are meant to run the software, right, and are meant to integrate into our lives or into some complicated machinery. And so I'm imagining that if I thought my software was complicated and had bugs,
right.
Designing chips is
the code. The
just
code
a little
is
bit more
very
detailed than
complicated
that, right?
to meet the requirements, and that's why we need good, skilled engineers, high quality design, high quality verification, and execution of translating it into the hardware. It's you need a good, high quality team and managers to manage that everything is in fitting each other. Everything comes on time. Everything is working together in good harmony to make sure that it's what we call till the end, till it works, till we ship it off to the factory.
Right. So the day-to-day of a chip engineer and the chip designer. I come to work in the morning. What do you do? What does a chip designer do when they get to the office in the morning?
Michael, after having the first cup of coffee, it's very interaction with your coworkers is very important to understand the requirements and how do I implement them? How do I implement the requirements so that it's efficient and it will function and there's minimum chance of a bug. So the understanding, you go to your work, understand what is the functionality that I have to implement in this block, or if it's a verification engineer, how am I going to efficiently test or verify that what the design engineer did and what the architect has defined that we have to do, how am I going to write the code that is going to verify that the design is really clean? And we have tools that we use. The more experienced engineers know how to effectively use these tools and write the code of what we call verification test patterns. And a lot of automation is in the process. We always think how part of the engineers' job is also see how can we do this more efficiently? Because as I told you before, every generation gets more and more complicated because we can put in more and more, we can cram in more and more features and performance. So we're always in the back of our mind thinking, how can I do this more efficiently next time? Or how can I do it even more efficiently now? And how do we develop tools, hand-on tools that we use to improve the development, to improve how we do verification, and much more and more efficiently, which is very important since there's the demand for resources is high, and the more efficient you are, also the better it's the cost to develop is much more feasible and challenging. So
revisiting the initial part of our conversation, which we were talking about the relevance of the field to today. If we're looking at where the world is headed, and I'm looking at a lot of my friends, and people are very quickly quoting Mark Andreessen's software is eating the world, and obviously computer science is one of the most popular degrees in most universities. As we're transitioning to the future, and where is semiconductors positioned with my generation, with the younger generation, as opposed to, let's say, software or other fields? Because honestly, I don't hear enough or as much about semiconductors in my day-to-day as I would like to. And just now I'm properly getting
Well,
exposed
one basic
to the awesome parts of it.
axiom is that software has to run on hardware. Okay, that's the basics. I always tell that to my software colleagues. Without us, you couldn't develop anything. So where do I think it's going in the future? I think that we are just going to have to think about supercomputing and how do we manage to there's a upper border. How much can we really cram into one chip? And we need to think, also us as the chip designers, how do I think of supercomputing? In other words, supporting multiple chips. Okay, and that started already. Multiple chips where we have to distribute all the performance requirements, not only in one chip, but on a farm of chips. Okay? And how we're going to do that in the future, communication between the chips is very critical, which is also being worked on. And that's the way I see it going forward. We are going to keep on developing chips, but because the demand is high, we now have to think about how we have more than one chip in the system, multiple chips in the system. How are they going to communicate with one another so that we can meet the higher demand for performance?
Fantastic. And Sandy, I really want to thank you for the time and the effort and the energy. I learned a lot and really enjoyed this conversation. So thank you very, very much for joining me. Best of luck with everything that you're doing, and it sounds fascinating, and I can't wait to learn more about the field myself. And stay safe and stay healthy. Thank you very much.
Thank you, Michael, for having me, and I'll be glad to come back whenever you want.